Today is on modeling the spread of schistosomiasis in human with environmental transmission. And I'm very happy to be presenting this work. Is a collaborative work. The first author is Marilyn Roho, a PhD student at University of Nairobi. We met in a workshop in South Africa, and from there we come up with this topic, and then we started collaboration. So it's quite a number of young African mathematicians that came together and tried to work on something. It took us some times, collaborations. It's not easy, but I really loved the experience. My name is Sansão Pedro from Eduardo Mondlane University, Department of Mathematics and Informatics. So with the link or the DOI for the paper, it can be retrieved through this link. So my presentation will include a short overview of the biological aspects of the disease, then the model setup, model analysis, and I will end with discussion on some conclusions. So schistosomiasis is an acute and chronic waterborne parasitic disease caused by schistosome flax or worms. Transmission of this disease has been reported currently in about 78 countries, of which 52 are endemic, and most of them in sub-Saharan Africa. By 2018, estimate of need of preventive treatment were around 229 million people, of which 90% live in Africa, and in this case, sub-Saharan Africa. There are about 5 species of the schistosome genera, which one is Mason, another one Japonicum, Mekongi, Intercalatum, and Haematobium. This work is more focusing on the Haematobium, since it's the most prevalent in sub-Saharan Africa. Schistosomiasis mostly affects poor and rural communities, particularly agricultural and fishing populations. Symptoms can be divided in the nature or in the 2 forms that we find in the schistosomiasis genera. For the first form, which I'll explain it later, the symptoms include abdominal pain, diarrhea, and blood in the stool. So these are the species that at their adult stage, they end up around the intestinal vesicula. Then we have the hematuria, blood in urine, fibrosis of the bladder, and urecta, kidney damage. So this is for the species that at their adult stage, they end up at the bladder or urine system. Schistosomiasis can be diagnosed through detection of parasite eggs in stool or urines. Okay. In terms of the biological cycle, this is one of the diseases with the most complex biological cycle. And this cycle involves at least 2 host species, humans and snails are the intermediate host, 2 free-living transmission stages corresponding to the larval stage of the parasite, one being Cercaria and the other one Miracidia, and also distinct environment. In terms of environment, it is said that for each species, schistosomes, and for each geographic region, there is a specific snail has the intermediate host, which in the general sense may say that the distribution of schistosomiasis, the geographic distribution, is much more determined by the distribution of the snails. Humans are the main definitive host for the 5 schistosome species that we have mentioned, but these species, after they have passed the larval stage, they can divide it in 2 forms that I mentioned before. We have those that goes when they are at their adult stage, that goes to the intestine. These species include Mason, Japonican, Mekong, and Intercalatum. Then we have the Esematobium, which at the adult stage, it ends up at the urinary bladder. So as a result of the parasite sexual reproduction in different human organs, the eggs pass through the vesicle or intestinal before they are excreted. Now I will be continuing with the epidemiology of the disease. Once the eggs are excreted in the water, they will hatch and release a worm that is named Miracidia, that soon will penetrate to the snail, to the intermediate host. Inside the snail, the Miracidia asexually will multiply, so it means it will replicate copies of itself, and in 4 to 6 weeks, hundreds of thousands of cercaria will emerge. Then this cercaria will complete the cycle by infecting humans when humans comes into contact with infected environment or infected water. Cercaria penetrate the human skin, causing local reaction. Most of the time, this reaction, it can be felt for region where the disease is not endemic, but in regions where the infection is endemic, generally it is asymptomatic. People do not feel anything. In the process of invasion, the cercaria will lose its tails. Then it will change into a schistosomula that migrates to the lungs or liver. Then in about 6 weeks, they mature to adult worms, they mate, then they descend to their final habitat, where it could be into the bladder or into the intestinal vesicula. The lifespan of adult worms is generally long, ranging from 5 to 10 years or even to more than 30 years. And this is the cause to reinfection. And the reinfection is also the factor that lead to different phenomena of the immune response. In general, we can visualize the biological cycle in this way. Let's say it starts from the eggs that were released from an infected host, in that case humans. They could be released through feces and urine for the type of schistosomiasis that at the adult stage, they go to the intestinal vesicula, or either through urine for the case of schistosomiasis hematobium, which they go to the bladder. So these eggs then will hatch and release Miracidia. Then is the Miracidia that will penetrate the snail. Okay, inside the snail, it will reproduce sporocytes that then will release cercaria. Okay, so cercaria, these are free swimming worms. So these cercaria are the ones that will infest humans by penetrating to the skin. Then the cercaria within in the human body, it will circulate, mature, and then it will release again eggs, okay? And those eggs, they will come out as we started here, either through feces or through the urine. So we can see it's a complex transmission cycle, and for myself, it was the first time to work on a disease such as this. It captured our interest, so we decided to come together as a group and see what we could do. Allow me to say that the work that I'm presenting here, it's a very simple, it's a very basic model, and the motivations are stated here. The fact that it is a multi-host system, it captured our interest, and also the fact that the environment may play a role at a time. We are attending this conference or the workshop, it was about climate change and other issues. Though we do not intend to model here the environment explicitly, but we include some of its impacts. And then the other thing about this disease is the host immune response. Here, when we say host, we mean the human, which is the main definitive host. And in this case, there is a phenomena of concomitant immunity in which human immune response is able to mount the larval stages of schistosomiasis, but fail to effectively control the adult stage. So we were intended to understand this, the interplay among concomitant immunity, reinfection. Why reinfection? Because in region where it is endemic, this has been common. And when we look at our settlements in sub-Saharan Africa, we see that we have more condition favorable to reinfection, kids playing very often in water boards and so on. So our interests were motivated by these factors. In terms of research questions, very simple questions that we thought we could outline them and try to understand them through a basic model. One is at predicting population level estimates resulting from interaction between concomitant immunity, reinfection, and environmental transmission, as well as looking at is it possible to determine contribution of different components of transmission to the level of infection in the human population, as well as determine the relationship between the epidemic threshold. Here, the much important one is the basic reproductive number and qualitative dynamics of model equilibrium. In terms of methodology, well-known mathematical techniques will be employed here or have been employed. The derivation of the basic reproductive number, the stability of model equilibrium. Then we perform parameter estimation using serological studies that have been reported in the region. Then we plot some time series. Based on our motivations, we outlined the following assumptions to construct the model. We'll consider humans as the definitive host. We are also going to include a non-human mammalian host, since the disease is much more prevalent in communities with agricultural and fishing activities. And within these communities, there is also culture of rearing animals such as cattle, buffalo. So we intend also to understand how these animals also they contribute as they also get in touch with the water environments. Then implicitly we model the intermediate host snails using the concentration of Cercaria. We did not model Cercaria explicitly just to reduce the complexity of the the model that would come out. We divide humans in 5 epidemiological classes that mirror the immune response, more specifically to include concomitant immunity. Then the force of infection is modeled using a Holling type 2 in the sense that we bring the biological effect that as much as we have more infective individual, then the infection will saturate. And we include also disease induced death rate in order to evaluate the morbidity and the mortality impact on the disease. But as well, this could be helpful when putting together scenarios of control, either in the human host or non-mammalian hosts. Here is the model flow chart. The H subscript stands for humans, and the C subscript is for Cercaria, and then the M subscript is for non-mammalian host. So the human population is divided in 4 compartments: susceptible, those who are vulnerable to infection but they're not yet infected, those who have been infected but they're not yet infective. And here we have those that are infective or newly infected, but they have not developed concomitant immunity. Once concomitant immunity is developed, then they will pass to this last stage. And once they are developed this, they will remain in this stage for life. And they will either exit through natural death or either due to disease in the long run. But then some of these individuals here, when they will recover with a temporary immunity, and they will again become susceptible to infection. And then the concentration of Cercaria is contributed by all the infective compartments or individual, the infective 1, infective 2, and the infective non-mammalian, which their dynamics are represented here. And for this non-mammalian, we are considering only 2 epidemiological stages, which is just the susceptible and infective. We did not include either exposed in order to reduce the dimension of the system. And then, as I said, we have here the force of infection, which is of Holling type 2, which is very common when we do this kind of modelings where we include animals, and also where we have environmental transmission, where at large numbers of effective individuals, the infection will tend to stabilize or saturate. Okay. From the flow chart, I think it is straightforward to understand those that come in, it is a plus; those that goes out, it is a minus. And where we have interaction, like we have this compartment interacting with this compartment, so this will be a product. So since it is a Holling type, this is then reduced by this term to saturate. So then we have these transfer terms. Like I said, the one that comes in is a plus, the one that goes out is a minus. And so each state, we look at it has a change in the rate. So that's why we come up with the derivatives, whereby we are looking at the variation at each compartment, how each compartment will be reduced or increased depending on system processes. And these system processes may depend on recruitment rate, infection, death, and also recovering for the susceptible. And for the exposed one, it is increased with infection, then it is reduced with development to the following next stage, which is IH1, and also through death, which is by mu age. The same process repeat. The compartment H1 is increased by those who leave the exposed compartment, and then it is reduced by those who leave this compartment, and so on. Having the system, it is interesting to analyze the feasibility of the region, positivity of solutions and boundedness, because we are dealing with communities, and communities do not just blow away in numbers, but they remain at some asymptotic values. So it is interesting to determine what is the feasible region here for existence of solutions to this system. So we stated the theorems, which says that the solutions of our systems, which are given by this vector, belong to this region, and they are bounded. The humans are bounded by this quantity, the cercaria are bounded by this quantity, and the mammalian, they are bounded by this quantity. Then what we do is that we apply the Birkhoff and Rotter's theory for differential inequalities, which is very common in this type of exercises when you look at the total population of your states. Why total population? Because what happened is just to split the total population in compartments. So when we look at the boundaries, we look at the total, because if the total is bounded, it means its components also are bounded. So from this total, clearly we can tell that this is less than this particular component, and then from which, since this is just a linear differential equation, this can be solved. And when we solve this differential equation, we can find out that the total population at any time, it is bounded by the maximum between the initial population and the end, this term. So we term this number by M1, okay? So now we intend to discuss the boundedness for non-humans. But one thing I forgot to mention for the non-human or non-mammalian population is that we consider its total population to be constant. You can see from here that we do not have the state for susceptible. Our system has reduced it to 6, to dimension 6. Why? Because since we assume that the sum of these two states is constant, then it means we can write the infective compartment for non-humans as this way, okay? So which means that the susceptible, it can be found when IM is known. So it means we can neglect it from our system. So in that perspective, okay, since this is constant, then it means that the IM will be less to the initial total population, which remain constant over the course of the dynamics. Now we are looking for the cercaria, which is the last equation, equation 1F. Now we want to discuss its boundedness, but we remember that the sum, which included these effective compartments, is bounded by M1. So it means each of them is bounded by M1. And then IM, we know that is bounded from here. So it means from the equation for the concentration of cercaria, we can tell that this term is less than this term. And again, this also is a linear differential equation that we can solve. As we solve, we realize that the cercaria population is limited by this maximum of these two, where C being this expression. So from here, we can tell that all solutions in this region are really bounded by the maximum of all these limits. Now, the next step is to prove the uniqueness of solution, and we make use of this theorem of uniqueness in the sense of Lipschitz continuity of function, so which is very common. I don't need to go into detail, and the theorem that we state is that the solutions, okay, these solutions at any time of our systems exist and is unique and positive for values that are greater or are beyond the initial conditions. And here we make use, how do we prove this? We make use of the Picard's theorem, which in general sense is to partition your given interval in small interval, and using the fact that the function is Lipschitz, so to prove the continuity. So if you repeat this process again and again, at the end, you find that you come up with the maximal forward interval of existence for the solutions, okay? And now making use of theorem 1 and of the lemma, we conclude that for any initial condition in this region, our system possess positive and unique solutions. So from here, it means now we have a model that is mathematically well posed. We understand that its solution will remain in a positive region. So we can proceed looking for the system equilibriums where this, in the long run, this solution will tend to. And we find that in our system, these solutions may approach to a disease-free equilibrium or to endemic equilibrium or a coexistence equilibrium of infection. In this case, the remaining compartments are zero. There are no infection here. So if we start, the question now will be, if we start around this point, are we going to remain, what are conditions to remain here, or what are conditions also to leave this state and perhaps go to another state, which could be the endemic equilibrium point. And the components of this equilibrium are given by this expression. And we can tell that once we know the value of lambda star, now we can tell whether this endemic equilibrium point exists or not. We have here this component D1, D2 minus gamma sigma. We also demonstrate here that this component is non-negative. So it means these solutions are positive depending on the value of lambda star. Okay, so in the next stage, we look for the value of lambda star that is a positive, and we find that this value exists and is positive when an epidemic threshold is greater than 1. And exactly this epidemic threshold, which is given by this expression, it is the expected average of secondary infection during the course of infection in the system, which is termed as R0. So which says that the equilibrium, the endemic equilibrium point, only exists for R naught greater than 1. Now we have obtained the expression for the basic reproductive number, but we also proceed on deriving the same expression using a general method known as, which employs the next generation operator approach. In this method, which is a general method for any system, using this method, you are also able to get the basic reproductive number. Eventually, or certainly, it won't be exactly the same as this one, because since this is a multi-host system, at the end, it will be a geometric mean of the new infections during the generation of the infectious period of each individual. And how is this computed? We have to look at compartments that are infective. So we can denote these compartments as X. Okay, so then we can find, we have a vector, and then from that vector of which represent the various stages of our system, and then from that system we can now find the Jacobian. Okay, and then we evaluate it at the disease-free equilibrium. Why disease-free equilibrium? Because the perturbation that we are looking at is from the disease-free equilibrium. We want to know if we are with a community without a disease and we introduce an infective individual, are we going to have an epidemic or not? So it should be evaluated from the disease-free equilibrium. So this matrix will be a matrix of appearance of new infection, and then this will be a matrix of transition, either out or in. As I showed in the flow chart, we have the arrows that go in and go out. So this matrix represents those interactions, okay? So from here, we have our matrix F and then our matrix V. These matrices are already evaluated at the disease-free equilibrium. That's why most of the components are 0, elements. But why are we doing this while we have already found this R naught? It's not that we are not sure that it is an epidemic threshold or is the correct R naught. It is indeed. But then when we'll be discussing the stability of the disease-free equilibrium, we will use a method that requires the use of these matrices. So that's why we repeat the process of finding the R naught using the next generation method. Then once you have matrix V, for you to have the spectral radius, which is the R naught, which is the largest eigenvalue of this matrix, okay, which is our R naught, then you will be able to compute it. So V, the inverse of V is given by this matrix, and then the product F and V minus is this matrix. So from this matrix, you can compute the largest eigenvalue, and that eigenvalue will be the resulting R naught. I'm not showing this expression because it has been already stated here. The only thing we have to understand is that it will be R naught square given by this, which means that the R naught that you obtain from here, it is not specific for particular type of infective. As you can see, in our system, we have infective from non-mammalian host, infection from Cercaria, and infection also from human. But it gives you the overall infection after a complete cycle. And a complete cycle, what could be? Could be from Cercaria, human Cercaria, could be from human Cercaria, then Cercaria, could be non-mammalian, human, then Cercaria. So all this interaction makes a complete transmission cycle. So the R naught obtained through this method does not offer our opportunity to do that. But at least we can look at the interaction and derive various components representing this interaction. So we have this component here, which we named it R naught 1. which correspond to interaction with the Cercaria and infective humans in compartment IH1. Then we have this compartment here, which correspond to interaction between Cercaria and infective humans in compartment IH2. And at last, we have this expression here, which correspond to the R naught of the interaction between Cercaria and the non-mammalian host. What does that mean? It means that here, this gives us the average number of new infection arising from that particular interaction. And as well, this gives us the number of new infection arising from that interaction. Also, this term gives us the number of new infections arising from that interaction. One of the, I cannot say disadvantage, but one thing which is particular about this type of the resulting R naught is the asymmetric behavior, because it is possible that the product could be less than one, while the elements of that, or the factors of that elements, not all of them are less than one. So when it comes to control, it's very interesting that we look at that. So here we are making more separation of the particular R naught for interaction between Cercaria and humans. It can be expressed this way, which is a product of what? Of new infections in humans arising from one infected Cercaria times new infections in Cercaria arising from one infected human of compartment IH1. Okay, so it's the same explanation, and here the specific expression for each term here. Now proceeding, having that and interpreted the R naught, it is important that we interpret the R naught well, because when it comes to application, we know which how various elements of the transmission cycles are captured in the basic reproductive number. Now we apply approach well discussed by Schwann and Pauline in their paper published in 2013, which provide us a way of proving stability of equilibrium point, in particular the disease-free equilibrium, using a Lyapunov function. We know for other methods does not provide us with a specific way on how can we construct a Lyapunov function, but through this method we are able to construct a Lyapunov function that is specific to our model, and use that Lyapunov function to discuss stability of the equilibrium points. So as you can see, which says that we can write our system, in particular the one of the infective compartments, but the whole system, this is just the reduction in this way. Okay, so this F is the same matrix that we saw before, and this V is the same matrix that we saw before, and then here F, which is a function of the, which will take care of the other components that are not included here. So if you are able to write your system this way, it means then you can construct your Lyapunov function, which will be a result of the Perron eigenvector. Why this Perron eigenvector? Because this vector is related to this matrix, the matrix FV minus. So it is Perron eigenvector, as we know from linear algebra, that for positive matrices, and we have seen that the matrices that we have there, matrices F and V, a positive matrix, and the product also FV minus 1 is a positive matrix, and the largest eigenvalue is R naught. So from there, we can have the Pedro eigenvector, and this will give us. So this is the theorem that we state, is that we can build the Lyapunov function in this way for our system. And we use this theorem to prove that the disease-free equilibrium point is locally asymptotically stable for R naught less than 1, okay? Now, like I said, the idea is through this construction to come up with the Lyapunov function that will help us to prove that when you take a derivative of this, okay, remember we had defined what was that our model was given by x prime. So when you replace here, you end up with this expression. And the idea is to show that the derivative of this Lyapunov function will be non-positive or will be negative. For this term is, we know that this, we're looking for this vector which is positive, this is positive as well, so this part will be negative. So we see that this one will be negative when R naught is less than 1. There is one thing that we added here, because when we are looking at the existence of the disease-free equilibrium and the endemic equilibrium, we had a lot of calculation there. I don't know if you remember, I can take you a little bit back. Here, we could not, I think, prove the nature of the other element lambda. So we had also to think about what happens does it mean that disease-free equilibrium does not exist if R naught is greater than 1 or not? So we include the Jacobian. We are considering the Jacobian of the system at the disease-free equilibrium. Done already. I think I should rush. I don't need to go into this detail. Then we discuss the stability of the endemic equilibrium. What we did here, we used the center theory just through using forward bifurcation to decide on the stability of the endemic equilibrium point when R naught is greater to 1, but very close to 1. So this is a method well known that was, I think, discussed by Chavez on his paper 2004, which is mainly saying that you evaluate you from that from your R naught at 1 is your bifurcation point, okay? And then from there, it means you'll be having a 0 eigenvalue. So that's what the method is all about. And then there are some calculations that we do to find these components A and B. We just change B here, B bar, to differentiate with the other B's that we had. And then based on the sign of these components, then we decide whether from R naught greater than 1, but very close to 1, are we having forward bifurcation or not? And we confirm that in this, we have forward bifurcation, which means that the endemic equilibrium point is locally asymptotically stable at that particular point. Then we did some parameter estimation from the literature, including serological studies, to estimate various parameters. As you can see, the number of parameters is large. It was a kind of a simple parameter estimation that can be retrieved from the paper. And then from there, we plotted some time series, and specifically when R naught is greater than 1. So these are typical behavior. These are typical behavior where then from the point of time, reduction on the susceptible, and then increasing in the effective population, all effective population increasing. So this is just a simple representation of what we would expect for R naught greater than 1. And from there, we vary some parameters. Those parameters we thought are important to be considered. Here we look at how the model output behaves when we vary some parameters, let's say alpha and delta, where alpha stands for the development of concomitant immunity, and the delta is the disease-induced death for the effective individual with cercaria. So these are typical behavior whereby if you increase alpha, okay, when you increase alpha, here we see that there is a reduction on the level of infection of IH1, but then for the IH2 there is an increase, and then interestingly we have a decrease for the cercaria. This is important because when it comes to control, we understand what is the effect of each parameter to model output, which is similar analysis that we do if you do sensitivity analysis. And then when we vary delta, we see little effect, but also shows reduction. So which would say is that if the more you can protect these individuals, it means you reduce the burden of the infection. And we do the same also for beta, and we have these effects where increasing a little of beta disease infection so directly impacts the prevalence of infection for almost all the compartments. And then another parameter that we show in the next slide is the AE, which is the escape rate of humans. So the escape rate in terms of control, look at it as if we are protecting the humans. So if we increase or decrease, what happen? So we see that increase of this rate, which means if we increase, it means they stay shorter time in this particular compartment, so they contribute less. So we have a reduction here on the infectives. And we do this for other parameters, which is pi e, b, tau, and then we come to the following simple conclusions, as our objective was to understand the interplay between concomitant immunity, reinfection, and environment. So we understand that the prevalence of infection is dynamically influenced by increase of the shedding of miracidia up to development of cercaria, promoting the growth of cercaria, increasing the environmental transmission due to cercaria, reducing the clearance rate of cercaria, as well as reducing the development of humans and non-humans mammal escape mechanism from cercaria attack. I think they are simple conclusions and my presentation, and from here, thank you.